Okay.
So hello everyone and welcome to the last medical science session of this term again. And today actually we'll be talking about something cool, and I hope in the breakout rooms and the icebreakers you had the chance to get to know each other. So today's topic is consciousness, existence, and extinction. So what do we mean by that? Actually, I think the topic itself is kind of clear, explaining the session, but I just want to preserve that complexity of the session name. And without giving any spoilers, I want to give the microphone to my fellow colleague, Sude.
Hey everyone, thank you. I'm just gonna share my screen and start it. And in the meanwhile, I just want to thank you all for opening your cameras and joining as much as you can. Is everything okay? Can you see it?
Yeah, it's working.
Yeah, it's working.
Okay, thank you. So today we're going to be talking about what is consciousness and some diseases that are related with it. Again, I'm Sude Çavdaroğlu, and this year's PR and external assistant at medical science. As always, you can reach me from my email about any question you might have. So let's start. What is consciousness? And consciousness in the vocabulary meaning, it means that an individual's awareness of self and surroundings. But when we check it pathophysiologically, it depends on the sensory input into the brain and the intrinsic activity of the reticular activating system. So it's about the descending reticular formation in the brainstem and its rostral connection, which maintain the cerebral cortex in an alert state. So there are some reasons of losing consciousness, and it can be a trauma, infection, and hypoxia, and it can be due to some diseases like epilepsy. And there are a lot of reasons, like some drugs that can make you, and hypothermia can actually make you unconscious. And what I want to state here is there's a Glasgow coma scale from 3 to 15, which states how bad your coma state is. That actually it is very commonly used in emergency medicine. Okay. So now I want to talk about understanding reality. I'm just going to give you one perspective about this, and we're going to actually have a big discussion after the slideshow. So according to the neuroscientist Anil Seth, he suggests that we are all hallucinating all the time, but we only agree about the hallucinations that we have, and we call that reality. I found it really intriguing at first, but then I actually listened to his TED talk, and I'm gonna add it to the references, and I really highly recommend you watch it. It really changes your whole perspective onto this matter. So what we have here is a box, and well, what I'm gonna ask you to look is the square A and the B, and what I wanna basically highlight is that there are some, like, at least I see there's a color difference amongst them, but he suggests that there are no color differences, and I actually added this as a reference, as an animation. And when you animate it, there comes this solution, and actually it looks both the same. And I was like, okay, this can't be happening. Like, this is so obvious that the A and the B are totally, different colors. But what the way that he explains this is that he says that there is a shadow due to this object, and because of this object, this shadow actually takes a more important place than the color. So we focus on the shadow and we see it as like that, because our visual cortex has already some expectations, and then when we look at again, we can't change the expectations, and we still see it. One is like light gray and the other is the kind of darker. So there were two more good quotes that I loved. that I said. It's just that when we agree about our hallucinations, we call that reality, which is a bit, you know, high thing to say, I believe. Like it's kind of breaking down our all prejudice, I believe. And also the second is that this means that even experiences of what our body is a kind of best guessing, a kind of controlled hallucination by the brain, which means that what we do is that we have like 10,000, let's say, predictions, and we just go through all of them in milliseconds and we choose the best guess and we live according to that. So basically that's all what I want to say about this, but I really, again, I'm going to say that you read and listen to the TED Talk. It has really good, perspectives. And I hope that we're going to talk more about it in the discussion as well. So now I'm going to talk about the diseases that occur when people lose their consciousness and or the understanding of reality. So we're going to start with schizophrenia. And as you all know, schizophrenia is a psychosis, typically starting around like 20 in ages. And it is important because people see delusions and hallucinations. And the important part is the clinical course. It can be acute, it can be treated, but most of the time it is just not cured, but treated, let's say. So what I found really interesting in that is the structural changes in the brain. Maybe you know that there are some hypotheses, and it mostly relies on the dopamine hypothesis, that our dopaminergic neurons play a essential role in the formation of schizophrenia. And there are some risk factors. I'm not going to be talking about them mostly, but just for you to know about them. The most important to me is that the enlargement of the lateral ventricles, and there is a decrease in the size of the brain. And also, obviously, the psychoarchitecture, which means like the neural and the synaptic organization is altered. And also that people may see that the white matter and the myelination can be affected. And there is no proliferation of the glial cells, so it suggests a neurodegenerative process. Also, another disease called delirium. What I'm going to focus, obviously, is that the clouding of the consciousness. And sometimes, like most of the times, it is worse at night, and it is supported by hallucinations. And because people cannot differentiate what is real and not, they are mostly agitated, and they have a bad concentration and memory in that manner. So common causes is some drugs, but what I want to focus is like kind of the medical conditions, like hypoxia can actually occur, and in organ failure, people can be in the state of delirium. So moving on to Alzheimer's. Alzheimer's is a progressive disease, as we all know, and it's a neurodegenerative disease. And it is the most common cause of dementia is Alzheimer's. So as you know, that they have this anterograde regression, and they have decrease in the recent memory, and also like some planning, and due to that they have changes in personality and behavior. I heard that some people actually think that they have someone stole their wallet because they actually forgot where it is. But what I actually want to focus on is the preserved skills, because I found it more interesting. It's because mostly about the cerebellum, that we learned it from, or how to listen, how to sing a song, or how to dance, which is I think it's really good. So that's what I want to talk about, like briefly, actually. So the other one is epilepsy, and epilepsy causes seizures and unusual behaviors, and most of the time unconsciousness. And it has some psychic symptoms as fear and anxiety. And when people wake up, they have this temporary confusion of where they are and how did this happen. And the last one that I'm going to talk about that can cause unconsciousness is head injury, and it can be anterograde or retrograde, but most of the time after a trauma, people may have unconsciousness for a little period of time. If it leads to a longer period of time, it's mostly coma. And the impairment ranges from a subtle slowing of thought and the distractibility through to a dementia. So this is what I want to talk today. Thank you all for listening. And these are my references. And as a feedback, you said that you want them right now, and I'm gonna be sharing them through the chat as well. So thank you for your attention. And now I'm gonna give it to Stella. Thank you.
Okay, thanks, Suda. I'm just going to open my presentation. Okay, can you see my presentation all right?
Yep.
Okay, perfect. All right, so I'm going to go a little bit more into the specifics of the neuroscience behind thought and consciousness, and kind of talk a little bit about neuroanatomy, neurophysiology, and kind of some theories that go along with that. So the discovery of neuroscience and cognition is actually, something that is not very old, because these processes were kind of only discovered within the past couple of centuries. And the way that consciousness was actually discovered was mostly by studies of language and language dysfunctions. So I'm sure everybody who has studied neuroanatomy is familiar with Broca's area and Wernicke's area, which are like the areas of the cortex which deal with language function and kind of language production and comprehension. And it was actually these two scientists, so this is Pierre-Paul Broca and Carl Wernicke, who by kind of studying these areas discovered language, and by discovering language discovered kind of how we think and our processes in connection with that. So to go over a little bit of functional neuroanatomy, I'm not going to bombard you here because we're all medical students, most of us at least probably, and we either have or will learn this. But just to give you a quick overview, brain function, brain areas of the cerebral cortex are kind of generally classified as either motor areas, sensory areas, or association areas. And association areas are kind of the ones that connect like motor and sensory input, and also are responsible for more complex functions such as motivation or thought, and all these things that we're going to go into in a moment. So association areas are specifically the prefrontal cortex, so in the front of your brain, the parietotemporal cortex, which is like at the back side of your brain, and the limbic system, which is kind of in the very center of your brain, and which is responsible for like emotion and memory and a bunch of integrative functions. So cognitive functions, so functions to do with thought processing, are primarily in the cerebral cortex, as I already said. So the like outer layer of your brain, which is gray matter, obviously. So as we all know, the brain is comprised of gray matter and white matter, and it's the gray matter that really is the one functioning in thought, pretty much. So to quickly summarize the like the functions of the respective brain lobes. So the frontal lobe is the one responsible for short-term memory, planning, and movement. The parietal lobe is the one that deals with somatic sensation, body image, and kind of the relation of the self to the external world. The occipital lobe is responsible for vision, and the temporal lobe deals with hearing, learning, memory, and emotions by extension of the limbic system. So the frontal lobe specifically has been found to be the part of the brain that deals with executive functions and decision-making processes and thought. This is something that we're going to go into later a little bit in Lara's presentation, but just to give you a short overview here. So these are sort of the functions of the frontal cortex: higher cognitive functions, goal-directed behavior, decision-making, and cognitive control. So like really control of thought, control of conscious thought. So to kind of go more into detail about cognition. So cognition is obviously thinking processes. It's complex thinking processes which arise from brain function in multiple areas. So the kind of current opinion and the conclusion that has been come to over years of research and different theories is that cognition is not a process of singular units or singular neurons. It's not an isolated process, but it's actually a very integrative process that combines different areas of the brain, different neuronal circuits, different neurotransmitters, and that it's really something that is much more complex than was initially thought. So it's not only just action and reaction, it's actually mostly some very complex feedback circuits that are going on here, some feedback and feed forward, and combinations thereof. So mental processes actually have been, have been discovered to be the process of interactions between the elementary processing units of the brain. So these elementary processing units are, again, units, so not singular organisms, like not organisms, but cells, but it's different parts of the brain communicating with each other in that way. So these different regions are obviously not only in one region of the brain, but they're really distributed across the entire brain, and also in fact distributed across both hemispheres. So hemispheres really are also during thought processes, during decision-making processes, constantly talking to each other, kind of like communicating with each other. So the left hemisphere and the right hemisphere are through neuronal pathways constantly communicating on cognitive functions. And it's actually not only functions that take place at the same time, but functions that take place in series as well. So you can imagine it kind of like in physics. I'm sure we've all had a physics class before. You can either have things that are set in series, so like you would have one and then the next and then the next, or you can have processes that take place at the same time, so parallel. And the brain functions are not only actually in series or parallel, but it's actually a very complex network that is much more complex than that, and is actually that actually can't be made as such a simple example. So it's really populations of neurons communicating with each other at the same time. And one more kind of argument to support this this thesis that cognition relies on multiple different bodies rather than just one kind of cell body on its own is that malfunction of single pathways, like any kind of brain pathology, can affect the information carried. So it can change the information, it can change the thought process, but many times, and actually most times, it doesn't disrupt the whole system. So it might alter it, but it doesn't disrupt it. And if something were, in series, so if it was just one cell, then the next, this would not be possible. So I'm going to give you a quick example of this kind of localist perspective. So the two kind of theories, one of them that every brain function is kind of at a singular place in the brain, and the other that brain functions depend on multiple brain systems and multiple areas. So this example is the so-called grandmother cell. What is the grandmother cell? It's actually just sort of a metaphor and something to kind of visualize this whole thing. So the metaphor goes like this. Your grandmother, we all, I mean, most of us, you know, have a grandmother. We know our grandmother. We associate certain things with her. We know her name, obviously. We know what she looks like. We know maybe what perfume she uses, what she likes to cook, all kinds of things. There are certain things from different brain systems that we associate with our grandmother. But is our grandmother saved in one single neuron? No, she's not. If this one neuron dies, will we forget our grandmother? Will we forget who our grandmother is? Of course not. So this theory is just trying to kind of visualize that there are multiple brain parts at play when you're trying to remember something, when you're trying to think of something. It's not just one singular brain area, not just one singular cell. There is no grandmother cell. There is no replica of your grandmother saved in one single neuron cell. And if that neuron is gone, your grandmother's gone. That's not how it is. So this is just a small example to kind of help you visualize this. And I didn't make it up, don't worry, it actually exists. And I think it's a really funny representation of this concept of localist versus modular kind of neuronal processes. So I'm going to touch quickly on the concept of self, because this is something that's really essential when we're talking about consciousness. So just as in any other brain process, we again have a modular organization of mental processes. So the self is just like the grandmother, not saved in one cell in your brain. It's really something that arises from the connections and from the different neuronal circuits, from the feedback and feed forward that goes on in your brain all the time. The sense of self is actually achieved through these connections of these independent brain regions. And one thing that's really important is something that I already mentioned, that it's the two hemispheres, so your left and your right hemisphere. Their communication is what gives you this collective consciousness. And something that's really interesting is that each hemisphere on its own, so left to its own, each hemisphere could have its own consciousness, could have its own thoughts. And this has actually been studied in patients where the corpus callosum, which is the connection between the two brain hemispheres, has been severed or has been split for any number of reasons. So in the specific article that I read, it was about patients with epilepsy who used to be treated by, by separating the corpus callosum. And the researchers ended up finding that these people who had a severed corpus callosum had sort of two different streams of consciousness. So for example, they would be reading a book, and the part of the brain that was reading the book with one hemisphere was reading it, and the other part was getting bored because it was just looking at the book. So things like that. There was another example of, you use your hand to pick up something, but the other side of your brain says no, so you let go of it again. It's really interesting, and it's quite interesting to see that it's really the connection. I think this is like the best way to actually visualize it. The corpus callosum, which is the biggest sort of connection, biggest sort of connective path between the two hemispheres, is what makes up yourself and your personality, your you, pretty much. So some little theories of consciousness. Consciousness is actually, as the topic of our whole presentation here kind of shows, it's not only a neuroscientific concern, but also a philosophical one. So it's kind of hard sometimes to draw the distinction between the two. But when we're talking about the neuroscience of consciousness, we're talking about the neural correlates, the neuronal circuits, and also some of the biochemistry that comes into play. So I have two kind of theories, or not really theories, but more like directions of consciousness in the context of neuronal circuits, in the context of neuroscience. So two scientists called Crick and Koch actually proposed that consciousness is something that is brought upon by a very small, specific population of neurons, maybe only like 1,000 or so, that are responsible for consciousness, specifically something like specific attention, or selective attention, or other processes like that. And then there's the other direction of scientists such as Dehane and Edelman, who have proposed that consciousness is more of a global property of the brain, where there's a big number of neurons at play, where it's really the feedback, feed-forward connections and complex circuits that make up this stream of consciousness. So some parts of the brain that are really essential in consciousness, and not only consciousness, but also this, like the self and your awareness, is the thalamus, which is part of the basal ganglia. So for anybody who doesn't know, the basal ganglia are some nuclei in sort of the very middle part of your brain, which are also made up of gray matter. So it's neuronal cell bodies, it's processing bodies. And the thalamus is actually like a collection of neuronal nuclei, which has become known as sort of the gatekeeper of consciousness. So the reason why this is so is that all thoughts that we have, all input that we get in our brains, so be that motor, sensory, or association input, has to pass through the thalamus in order to reach our consciousness. So in order for us to become aware of something, it has to pass through these nuclei, be kind of processed in there for a moment, and then it's passed on to our consciousness. It's important to mention that there's one exception to this, and that is olfactory fibers. So our sense of smell actually does not have to pass through the thalamus. It goes straight to the limbic system, which is obviously where we process emotions. And that's why sometimes we have such strong emotional reactions when we smell something. And I also think that this is a really interesting fact, because I think it's something that most of us have realized before, be this, I don't know, smell of a place, food, something like that. Some people just have really strong emotional associations with certain smells. And it's really interesting to know that there's actually a scientific background for this. Yeah, so to go back to the thalamus, the thalamus has integrative and conductive functions. So the thalamus itself processes, but it also passes on. And it's kind of, it acts as a filter of thoughts, because even in, for example, sleep states, the thalamus is the one that filters out thoughts from the outside. The thalamus shuts out other impulses, and also shuts down our own sort of motor impulses at the time, in order for us to remain in the sleep state. So as a short conclusion for this connection with thalamus and basal ganglia organs, is that consciousness is not only part of the cortex, but it actually arises only through the connection and through the communication between the cortex and subcortical regions, such as the basal ganglia and other nuclei. So to kind of go a little bit, touch on the kind of biochemistry that is behind consciousness and thought, and something that we can observe, because obviously the brain is not something that we can just easily take biopsies of or easily kind of examine, such as we could many other organs. But something that we can see on brain scans, such as PET and MRI, are that the metabolic demand of the brain increases in areas where we're thinking, where we're actually processing, and in areas that are in general active. So some parameters that are often measured are blood flow, and also blood oxygenation level. So for example, you can take a so-called bold MRI, so that would be a blood oxygenation level dependent MRI. And this is often used for kind of analyzing thought, analyzing your level of neuronal activity in certain brain regions. Yeah, pretty much this just shows us that the biological and biochemical correlates are necessary for measurement of neuronal function. These are some of the few ways that we can actually, like visualize that, because as I just said, it's kind of hard to do so with the brain, but there are many advanced technologies that are available nowadays. So lastly, to go a little bit into neurotransmitters, to kind of round off this biochemistry lesson here. Neurotransmitters, specifically associated with thought and consciousness, kind of hard to say, these neurotransmitters are, these neurotransmitters are not, because many neurotransmitters are universal kind of in the brain. There are obviously regions that have more of certain neurotransmitters and more of the others. Also regions that are very specific to neurotransmitters. But many times it's the specific cell, many times it's the specific receptor that determines the actual function and the actual effect of a neurotransmitter. So for anybody familiar with dopamine and dopamine's receptors, dopamine has two kind of types of receptors. So there's the D1 type, which kind of activates cells, and the D2 type, and also the D3 and D4 subtype, which kind of inhibit cells. So it really depends on like where dopamine is going to bind, on what receptor it's going to bind, what receptor the cell has. So as you can all see, this is kind of something that's more complex than just which neurotransmitter is there. There's no, I don't know, memory neurotransmitter or thought neurotransmitter, but it really depends on the complex integration of multiple neurotransmitters at multiple times, at multiple sites and receptors as well. But in general, one thing that can be said about neurotransmitters in the context of thought is that monoamine neurotransmitters have been found to be really important here. So that would be dopamine, serotonin, and noradrenaline or norepinephrine. And some of the processes that these are involved in are just these cognitive functions. So memory, executive functions, as well as arousal and concentration. And something that's interesting is that these have actually been researched in the context of neuropathology. So as Sude mentioned earlier, schizophrenia is something where consciousness is altered. So it's really interesting to study which neurotransmitters are affected in the context of schizophrenia, and how these can kind of be found to affect the disease process, and how they can then also kind of translate into the physiology of them and be kind of discovered in that way. Okay, so with that, I'm at the end of my presentation. Thank you everyone for paying attention, and I'll be happy to take questions maybe at the end, but feel free to write it into the chat box at any time. I hope you enjoyed this part, and I'm now gonna stop sharing my screen and pass on to Lara, who's doing the next part of the presentation.
Yep. Thank you, Stella. That was amazing. Let me bring my presentation. Okay. I hope you can see it. Okay. All right. Hello, everyone. Thank you so much for being here. My name is Lara. I'm the Health Policy Capacity Building Assistant, and I'm super happy to be a part of this e-session team. My presentation is going to be a lot simpler than Stella's. Biochem is always the hardest part, in my opinion. Mine is going to be a bit more verbal. And I'm going to talk about, obviously, the process of making decisions and what kind of plays into that. So the first thing that might come to our minds when we say decision making is the survival instinct. And that has been like a part of human cognition for a very long time. And evolutionary psychology, there's this funny quote I found on Harvard Business Review that says you can take the person.
Lara is here. I think she is already
Sorry.
here. You know.
Yeah, my internet cut off. I'm so sorry.
Okay, no problem at all.
I'm gonna continue where I left off. Okay, can you see my screen now? Okay, I see some nods. Okay, wonderful. Yeah, the survival instinct. I found this quote really funny, so that was what I was talking about. And evolutionary psychologists obviously don't say that we're all the same, but they argue that even though humans have come a long way from being in the agricultural period to our modern civilization today, human evolution might not have kept up with the same pace, and we still have this survival fight or flight instinct back in our minds. So this sort of like static makeup might have a role in how we view and act in our world today. And these studies might also suggest that emotions cannot really be suppressed at any time. And that might be one of the biggest reasons why it's so hard to like receive and give feedback, because emotions like seep into every decision that we make. And obviously it's quite simple, but survival instinct might not be the best decision maker in today's day and age, because it's far too simplistic to make our decisions that way. And it's not efficient to overcome many of the challenges that we are confronted with today. And we have a quote here from, let me see, Daniel Kahneman. I'm sure I'm butchering his surname, but it's basically about how we think has evolutionary value, and that, you know, we have these cognitive biases that don't always give out the best outcomes, but might be, in most cases, what's sufficient in terms of time and energy, hence survival. But in general, like I said, the fight or flight response is far too simplistic to be generalized in our world today. All right, so let's continue. And another thing that has a huge role in the way we make decisions is our identity. And that gives us the attributes that affect our daily behavior and every single decision that we make. There are so many perspectives on this, and I am in no way an expert on decision making. So I am just gonna try to summarize some of the views on this, which one of them is from psychoanalyst Erik Erikson, who, you know, considered, oh gosh, my connection is unstable again. But you can hear me, right? Okay.
Yes,
Great.
we can hear you.
Wonderful. Yeah, Erik Erikson basically considered our identity to be psychosocial in nature, and it is not something that one can resolve once and for all during like adolescence. It's something that one has to think about continuously throughout the lifespan. And studies have shown that identity status and global self-esteem, which, you know, obviously affects many of the decisions that we make, are directly correlated, according to a paper published in 2013. And unless I made the horrible mistake of forgetting, most of these studies will be linked in my references, which I'll share with you at the end. And another study into adult attachment styles and relationships in relation with identity development, and also show that, you know, cultural contexts of belonging and the ways in which we are presented with choices may be more influential than identity formation. All right, so what does decision making actually mean, and what do we do when we're making a decision? This is a field, especially decision neuroscience, is quite new, but it has exploded, and there's so much research on this. And if you're in any way curious, I definitely suggest that you check out any of the resources that I will provide in my references, especially a specific study by MIT scientists. So it's natural to think, that we're staying logical through every decision. And actually, I used to think that being logical was the ultimate goal when I was watching this series, Bones. I'm sure some of you have watched it because, the main doctor there, she seems like the perfect human. She makes the most logical decision at every time of the day, but we can only stay, emotions seep into every decision we make in every day, and we make hundreds of decisions, some of them unconsciously. And our thoughts, even though they're abstract and vaporous in form, are determined by the actions of specific neuronal circuits in our brains. And this interdisciplinary study is known as decision neuroscience. And it's focused on uncovering these circuits and mapping thinking on a cellular level, which can obviously help us figure out how we actually make decisions and what it looks like in the brain. And one of the most practical outcomes of this type of research is understanding different types of mental disorders, including depression, anxiety, schizophrenia, and so on. And this quote you see on screen belongs to a Dr. Lee from Yale University, and he studies economic decision-making. It goes, the essence of the thinking during decision-making is mental simulation. You're trying to predict before you take an action what outcome may occur based on your previous experiences or by observing and remembering the outcomes of other people's behavior. So this can also be related to reinforcement learning, which is a huge effector of decision-making, but I will try to go into that a bit later. Let's move on right now. So, like I said, lots of research has been done into the brain activity during the decision-making progress, but one that stands out to me, which Berkay suggested in one of our meetings, is a paper by Soon et al. From 2008, and that's about the brain activity in different cognitive regions that can help which decisions one will make about as much as 10 seconds before these decisions actually become conscious to you. So they tested, I don't exactly remember the experimental design of this study, but I think they made participants make a choice between, left and right, and, they chose which color the text was when they made the decision. And actually some of their brain regions were fired up 7 to 10 seconds before they said they were conscious and they actually made the decision. So for some scientists, this has been a topic of debate. More knowledge about the workings of the brain can mean a lowered likelihood of exercising free will when making choices. So they can argue that mechanisms might seem to displace freedom, which is interesting to think about. And another thing that has been studied within decision making is the issue of noise, and that's, to my understanding, is the fact that neurons do not convey the same amount of action potentials per unit time, even when they're exposed to the identical condition over and over again. At least that seems to be the observation in the laboratory. But there doesn't seem to be anything magical about this noise. It doesn't, seem to give you free will to decide or anything, but it does seem to affect the way we make decisions. And some people are thinking about whether it reflects fundamentally deterministic or indeterministic processes. So in summary, if we can decipher the basic blocks that lead to the outward event of conscious decision making, which are in essence neurons and the process of synaptic transmission, we can put together we can put them together to explain and understand complex human behavior. And decision making is so hard to study because of this. There are so many psychological and anatomical, physiological elements that play into how we make decisions. Okay, I'm being unstable again, so I'm going to try to end my presentation as quickly as possible. And like I mentioned before, the process of reinforcement learning, as per the Dr. Wang of Yale University, they believe it plays a central role in decision making, and that's basically, I'm quoting, when you're not explicitly taught what you're supposed to learn, but rather learn it by trial and error and by getting feedback about how well you predicted the outcome. So there is a substantial body of work showing that the neurotransmitter dopamine plays a central role in reward signaling, which Stella talked about, and that it can affect changes in synaptic connections between neurons in a way that's consistent with reinforcement learning, which then plays into how you make your decision. And the last thing that I would like to talk about, which I found super interesting, and I will share the link with that study with you, is one that was done in MIT, and that investigated how one makes a big decision. And that's basically comes down to hierarchical reasoning. And I think Stella also talked about that a bit, which is when we break a problem down into smaller series of decisions. And, first the brain tries to compute the confidence over the outcome of each decision, to figure out which one will likely result in failure. And then you need to, if it is not easy to discern the cause of that, the brain makes additional attempts to gain more confidence about the decision it's about to make. And I apologize if you can hear children screaming. There are a lot of kids that live around my house. And these computations are performed using a distributed network of areas in the frontal cortex. So like my teammates also told you, none of this is a work of an isolated single neuron. So it's not your grandmother neuron deciding and determining your every decision. All right, I think that's all I wanted to talk about. I'm sorry if it was kind of all over the place, but like I said, I just kind of wanted to talk about the very interesting things that are happening in this field. Thank you so much for your attention. Here are my references. I will also put the link in the chat along with the MIT study, but that's also in the references, just in case if you want to check it out really quickly. Thank you so much.
Okay, perfect. Thank you for sharing the screen, Berkay. Do you hear me? Okay, perfect. So hello, everyone. My name is Nila Koch, and I'm the Medical Science Research and Internal Assistant. And now I'm going to be talking more about what happens to the brain after death before we go into the discussion afterwards. Okay, so you've probably all seen this before, but brain death is defined as the irreversible loss of all functions of the brain, including the brainstem. And this means patients will not regain consciousness or be able to breathe without artificial life support. Brain death is also legal death, and therefore after brain death, organ donation becomes possible. Okay, so now going into the clinical decision of brain death. First of all, it's important to mention that there is no global consensus of diagnostic criteria, but countries have similar algorithms usually. And normally more than one physician is necessary to declare brain death. There are 4 common steps. The first one being that there is evidence for irreversible brain damage of known etiology. So you need case records or past medical history of the patient. Then it's important that you can exclude reversible causes of coma and apnea. I'm also going to talk about this later. Again, it's a really important step. Then doctors perform neurological tests, including tests for absence of brainstem function. So for example, they check that there is no pupillary reactivity. And then lastly, there needs to be an observation time to prove that the damage is irreversible. So for example, the country that I'm from, in Germany, if an adult has a primary brain injury, they need to be observed for 12 hours before you can diagnose irreversible brain dysfunction, and therefore you can, before diagnosing brain death. And when you talk about secondary brain injury, you need to observe the patient for 72 hours. Alternatively, doctors can also use further technological examination methods like EEG to immediately prove dysfunction. Okay, so now moving on to the next slide. Is brain death reversible? So I guess you all have seen like articles in the media with people who were diagnosed brain death but actually woke up again. And I think 2 really popular cases were, first of all, Trent McKinley and also Stephen Thorpe from Great Britain. So first of all, talking about Trenton McKinley and what happened there. He was a 13-year-old boy from Alabama who was diagnosed brain dead in 2018 after suffering severe brain trauma. He eventually suddenly regained consciousness just after his parents signed the paperwork to donate his organs. So there was a lot of outrage. And the possible mistake during his brain death exam, so why he was falsely diagnosed brain death, was actually that his body temperature of was only 26 degrees. So before I talked about excluding reversible causes of coma and apnea, and actually having a low body temperature is a reversible cause. So he shouldn't have been diagnosed brain dead, and there was simply made a mistake by doctors. And also talking about the second case, the guy on the right, whose name is Stephen Thorpe, when he was 17 years old, he was in a car accident in Great Britain in, I think, 2012, and he was diagnosed brain dead after 2 days in the hospital. However, his parents wanted a second opinion and asked an external neurosurgeon for help, who found faint signs of brain activity. And 2 weeks later, Stephen woke up from his coma, and within 7 weeks, he was able to leave the hospital. Again, in this case, there was also a mistake that was being made, and the probable cause of why what went wrong in his exam is that the doctors didn't pay attention to his medication, which might have caused the temporary failure of his brainstem. And what's also important to note about this case is that in Great Britain, brain death equals brainstem death. So in most other countries, your whole brain needs to be dysfunctioning to diagnose someone as brain dead. But in Great Britain, just if your brainstem doesn't work anymore, you're brain dead and your organs can be donated. So to say in other countries, he would have never been diagnosed as brain dead. So nevertheless, you can see that it's crucial to always do brain death exams carefully and pay attention to detail. And also brain death, sadly, if diagnosed correctly, sadly, is not reversible. Okay, so next, I'm going to be talking about more about the chemical reactions that occur in your brain when you're dying. So I probably also guess you've heard of like people seeing white lights or having out-of-body sensations when they have near-death experiences, which seems kind of weird because most clinicians would assume that the brain after clinical death is inactive or at least hypoactive. So they couldn't really explain these experiences. But actually there were studies that showed the complete opposite to what people usually guess of the brain being inactive when dying. For example, there was a study on rats in 2013 that showed a transient surge of gamma oscillation within the first 30 seconds after cardiac arrest. And this frequency band exhibited a striking increase in anterior-posterior directed connectivity and tight phase coupling to both theta and alpha waves. So interestingly, high-frequency activity in the near-death state exceeded even levels found during the conscious waking states. So they kind of concluded in the study that there is a heightened conscious processing at near-death, which might give us a biological basis for the experience that many people describe. Okay, and moving on to the next study I'm going to be talking about, because the first study, obviously it was in rats, so people were not sure if you can transfer it to human brains. But there was a study in 2018 conducted in Berlin and Cincinnati with 9 patients, which goal was to kind of predict the time available for resuscitation until irreversible damage. And they found a non-spreading depression. So that's defined as the silencing of of spontaneous electrical activity during the steep falling phase of oxygen level in the brain when the people were dying, which could be explained by oxygen sensors in the brain. And then afterwards, they found again, as compared to the study in the rats, for example, a terminal spreading depolarization, so a higher activity in the brain, starting 4 minutes after non-spreading depression and onset of the final drop in perfusion. However, anoxia-triggered SD, so spreading depolarization, was fully reversible without any signs of cellular damage if oxidative substrate supply is reestablished before a certain commitment point, this commitment point being defined as the time when neurons start dying under persistent depolarization. And the delay between SD onset and the commitment point can actually range from a few minutes to over 10 minutes, depending on very many different variants. So they kind of concluded that onset of the brain's terminal SD does not mark the onset of brain death. And there's presently no indicator that can determine when terminal SD becomes irreversible. So to kind of conclude this, they didn't reach their goal to find out when restoration of function is no longer possible and therefore resuscitation can be stopped. They didn't reach that, but I think it's still really interesting what they found in the study, and it gave us more of an insight into the reactions that occur in the brain when it comes close to death or when it's dying. So yeah, that concludes my short presentation about death in the brain. And yeah, if we can move to the next slide here, you can find my references, and I can also send the 2 studies that I talked about mainly into the group chat. And if you have any more questions, feel free to ask, and thank you for listening.
So I think there we come to the last part of this session, the discussion part. But before the discussion, actually, I'll start the lightning of the discussion, I can say. So let me share my screen again. And okay, there we go. I hope everyone can see my screen at the moment. So I think everybody should have heard about this one, the Neuralink right now. The project that Elon Musk's kind of advertising at the moment. And I think his latest breakthrough technology for the brain, as he also says, and there was also a live program of him showing the experiments regarding the Neuralink. So at my part, I want to ask the question to all our participants: will our existence cause our extinction? Because why? I think this part will create so many questions. So we talked about what consciousness is, how is the biochemistry of consciousness, and after that, how the decision making works, and actually what is that, and what differs the work of brain with a brain that doesn't work, basically. So in this part, what I want to talk about you, I didn't prepare any presentations for you, and just what I wanted to show you is the Neuralink's website. And before that, I also want to remember myself again. I'm Berkay Akat Ülker, the Medical Science Director for 2019 and 20. So going into like exploring the website of the Neuralink, let's first go to this part. So as we all told, in the website of them, they show the basic stuff that we already told you. And actually these stuff are really basic for medical students. But as you can see, actually they're basically going from the neuroscience and the neurons communicating through electric signals. That part is important for us. So, okay. I thought that there was something in the chat. So they say that they can record electrical signals in the brain. So that comes to the other part, like why do electrodes need to be connected directly to the brain, and how does neural stimulation work? They also give some information about that. And the most important part here is the EEG about the neural link. So basically, the electrodes in the brain can work as the non-invasive techniques such as EEG, and therefore we can monitor the brain signals. And the monitoring of the brain signals can help us actually use some kind of brain-computer interfaces. So how does neural simulation work? As you can see here, actually there are some examples and the electric fields. This is actually physics, and this is a thing that you should read if you're interested in. But basically, it says, by stimulating in the right temporal sequences across many electrodes, it is possible to create patterns of activity that elicit a desired sensation. As we say, for example, the feel of an object in the hand or a visual image. So this is how neural stimulation works. So let's just get into the interfacing with the brain, how we can create brain-computer interfaces. And actually, this is a technology we already use in science. So this is an innovative thing, but there are already created brain-computer interfaces for the prosthesis and also for the understanding of the human brain, but they don't work exactly with invasive procedures. So the Neuralink, what Elon Musk has found, works with an invasive procedure. It is directly implanted to the temporal lobe of the brain with this special surgery. So you can see the link here, as they can say. There are some images on that, and actually, this device is as small as this. This is really innovative, and I don't know if you can see that part of the website. So here is the link that we're talking about in Neuralink. So this is basically a computer, a very little computer, and I think we can say it's barely 1 centimeter in diameter. And as you can see, there is the neural thread, which is, we have the electrodes here, which are really small, and we have the charger, and you can actually, I think, wirelessly charge this thing. So this is really the future itself. So as you can see, this is the apparatus that we use to implant in the brain. So how did you implant this thing? Again, they have their information. And also, if you want to discover more, you can actually go inside more. Personally, I have a special interest in brain surgery. So in the neurosurgery, there is a precision automated neurosurgery. And basically, this is how it works. It's not really invasive. It's, I think, as they say, in 10 minutes or something like that. So they basically implant it to the brain and it's done. That's it. Like it connects with the brain instantly with this special kind of surgery. And also the company improves that special kind of type, robotic surgery. So even more, there is the Neuralink app that they want to create in the future. So that is kind of really interesting if you're interested in the wearable devices. And I know that there are some people who are already interested in health policy and wearable devices regarding the digital health. So this is, again, something really interesting. Just the thing you want to do in this app is basically thinking about what they want you to think. So basically, when you try to synchronize your iPhone, for example, with Neuralink, you have to think the same thing. For example, it says like, just think about this emotion, and if you think about the emotion, it makes you learn about the work of Neuralink, and it collects your signals of brain, and with that signals, it lets you to do much more things. For example, there are things like that. You think with your brain, like, I want to go to this position and to this position, and the app trains you, and also the app learns about your way of thinking. So learning about more, what is Neuralink developing? I think it is a thing that you can read. So here you can see there are the challenges with the Neuralink. It's the electrodes, because it is, again, about the electrics and some basic physics, actually, that you can remember from high school. The most important thing about the resisting corrosion from fluid in the tissue. This is important. And this is actually the problem with lots of implants that we have in the human body. Then we have chips. And again, this is really important. Neural signals in the brain are small. They're like microvolts of signals. And the scale on our devices requires on chip real-time identification and characterization of neural spikes. So the characterization of the spikes are really a hard thing to do, because actually in the sleep labs, if you work on that, even on the sleep labs, this technology is something high, and the high yield technology barely can identify those signals. However, they say that they can manage that in the future. And again, the hermetic packaging, this is really important because basically you have to have a computer at this level and you have to implant lots of things into that computer. Again, this is a challenge about Neuralink. The neurosurgery itself is a challenge. I'd say that it's only a single 8mm skull opening, but again, it is surgery. Just wait. Yeah. So it is surgery, and surgery itself is a hard thing, and it's brain surgery. It's not a simple surgery here. And also the neural decoding is important itself. So again, I'm coming to the point that I want to create the discussion. So let's just move to the engineering with the brain part. And also you can just enter this website and read. So the thing is, they want to create a direct link between the brain and everyday technology. The future of neural engineering, they say, as we talk here, the auditory cortex, somatosensory cortex, they want to have a collaboration between these parts of the brain neuroanatomically, and I won't be gaining so much on that. But again, here are some questions that I want to ask you. I won't show you the answers because the answers are really simple for you to find them. So the questions are here. What will the link do? Actually, this is something that you can learn here. Actually, it's about the connection between user's computer and like with some Bluetooth connection that they want to create. And actually, it will be working like a game controller. But who will the link help? Basically, it will help all the human beings, but their main aim is to fix the spinal cord injury. For example, there are those people with ALS, let's say. I think the most important example here is Stephen Hawking, who had to create his computer with a really small thing that he had, and even that technology was innovative at his times. But right now, what they want to have is to make people control the computers with only their manpower. And even more than that, they say that they can cure depression, they can cure Parkinson's disease with those special signals, and also they say that with the prosthesis to people, they can make people just think about the movement, and with their brain power, then they can make those prostheses work and nothing mechanical. Right now, all of the prostheses work mechanical, actually, lots of them, I can say. So the questions are here. Will the link be safe, and will the link of future systems be available to healthy people? And also, how will you address device security? This was a thing that we wanted to talk yesterday in the yesterday's session. So what I want you to discuss is, right now, there are so many conspiracies regarding the Neuralink company. Like, are they going to be inside our brains? Are they going to be hacking our brains? So if, like, just think that in the bank accounts, if someone hacks your bank accounts, your ID or the other stuff, it's actually something safe because you can just close your bank account and open a new one and just transfer your money to there. But what about your personality? Will be your thoughts of you creating them. For example, we talked about the P30 waves, and I think that's another thing that should be talked about. With those waves, we learned that actually your decisions are made in your brain just milliseconds ago, before you do the decision itself. So will you be controlled with that chip if you're hacked? And are you going to be even able to understand that if your chip is hacked, and if those are the thoughts of yourself or another one's thoughts that just want to steal your ideas? So this is something important. I just create the questions, and I hope that you will be having some fruitful discussions here. Before the discussion, what I want to have is, again, to share you the link for the participation and attendance here. And I think we can close the recording here, Lara, if you want.